today we're going to have an introduction to target maximum likelihood estimation of causal effects, and it's presented by me, Susan Gruber. I am a biostatistician, and I have been working in the field of causal inference and machine learning since my days at Berkeley, where I was Mark Bondolon's PhD student. And more recently, I've spent the last 5 or 6 years in different positions and involved in a number of different Sentinel work groups and FDA work groups. Today's talk, I want to give you an introduction to TMLE so that you can understand why we are trying to say that this is a good solution to the problems that you might be having. The whole thing is motivated by the fact that we want to learn something about the world from data. And in our traditional training, we have all learned how to use a parametric modeling approach. And so suppose we want to evaluate the effect of some treatments that I'll call A on an outcome I'll call Y. Well, you can see this woman on the left says, oh, it's a binary outcome, therefore I will use logistic regression and I will estimate the odds ratio. And then the person on the right thinks, well, we've got some people followed up for different lengths of time from others, so I'll use a Cox proportional hazard model to estimate a conditional hazard ratio. Neither one of them is wrong. Neither one of them is necessarily right. They're just bound by what they've learned, and they're both thinking about some model that looks something like this, where there's a beta 0, a beta 1, the coefficient in front of treatment in the model, and then adjusting for some covariate. That's typically what's going through their minds because that's what they have available in their toolbox. And typically, there'll be just a main term coefficient in front of treatment because if there were lots of interactions, if the effect of treatment on the outcome had to do with comorbidities or with other drugs that the person is taking at the same time, that might actually be true, but it would make it really difficult to interpret because there would be multiple coefficients in front of terms that had A in them. And so people think, well, I'll just do this. It's some kind of average over everything without knowing necessarily what kind of average over what they're talking about. So this approach assumes a convenient parametric form that precludes effect modification. And it also, in the case of this Cox model, it turns a blind eye to informative loss to follow up. Like I guess in case of the logistic regression model as well, because in logistic regression, you would be stuck doing a complete case analysis. And with a Cox model, yeah, it can handle different amounts of follow-up, but the assumption is that those differences are just uninformative. It's not due to drop out for some reason that affects the outcome. And that is maybe true and maybe much more likely to not be true. So this is what we're stuck in right now, and there's better ways to look at it. So targeted learning from data, you heard if you tuned in last month, you learned about from Mark with an overview, and there's a roadmap. How do you even think about a problem? You start with a well-defined question, and then instead of jumping to a statistical model that's maybe a Cox proportional hazards model or logistic regression model, and being shoehorned into, therefore I must estimate a hazard ratio or I must estimate an odds ratio, we can just step back and say, well, what do you really want to know? So we're going to instead define the causal effect of interest as a parameter of the underlying probability distribution of the data. And if you ever look at any TMLE papers, P0 is the true underlying probability distribution of the data, instead of as a coefficient in a specific model. And that right there frees us up to just think about what is it we really want to know rather than, how do I interpret that coefficient? What did I learn, in my first stat class? So to think about it this way, there's different ways to do it. And today, I'm just going to go over the counterfactual framework for thinking about these causal models in something we call the full data. We'll get to that in a few slides. This counterfactual framework, though, is conceptual. It's not real. In reality, you're going to just observe the data you get. There'll be the outcome, the treatment, and the covariates on the person that you've measured. So you've got to make some assumptions that connect the conceptual data to this, what you have in real life. And we'll talk about those too. But the bulk of it today, we're going to talk about this step number 4 in the roadmap, estimating the causal effect you're interested in from data, excuse me, using TMLE and superlearning. So I'm not really going to talk about superlearning today, just a few sentences. Next month in April, we have our next webinar series will be an introduction to superlearning. So today's real focus is on how we're going to use TMLE to estimate our causal effect from data. And once you have the estimate, you get some kind of statistical conclusion. You know, this thing is a statistically significant result or it isn't. These are the confidence intervals, 95% confidence intervals, for example. And from that, you can draw a scientific conclusion. So those are the steps in targeted learning from data. Okay. So I want you to know about TMLE today. That's my goal, and I've got 50 minutes. So TMLE generally is a very broad general template, and there's a whole bunch of theory underlying it. And when you want to use TMLE for a specific problem, like I want to know the risk difference or I want to know a hazard ratio, then how you do it, how you instantiate this, it will be a little different depending on what it is you want to estimate. No matter how you do this, you do it right and thoroughly, and you can generate reliable, interpretable evidence that you can use for decision making. So that's great, but it doesn't really help you understand how does it work, what is it? And you can't really, you don't know how to trust the evidence that's generated if you don't even know what's going on. If I just, you just give me data and I give you an answer, and then you're supposed to make regulatory decisions from that. It's pretty hard to put your FDA hats on and do that if you don't even know what it's doing, what TMLE is doing under the hood. So I'm going to try to peek under the hood today just enough so that you say, okay, I get it. I feel good. I understand what this is doing, and I would be really willing to move forward and make decisions based on the evidence provided by TMLE. So to do that, I'm going to be a little less general and a little more just concrete. I'm going to use one specific example of the additive treatment effect or the risk difference if the outcome's binary. And so we're going to sacrifice a little of the generality of TMLE to make some very clear, simple points. Because when I'm done, my hope is that you'll get how it works, and then you'll say, oh yeah, so I see how that would work if we have, correlated data from different sites or different medical, physicians or something. Or I see how that would work if I had missing outcomes. Like you would just extend these simple ideas to these more complicated settings. But for today, we're just going to stay in this very simple framework because, as I say on the slide, the math is going to be sophisticated, and there's no point in looking at that, but the principles are very understandable. So that's what we're doing today. Okay, so let's start. The first thing I said was we're not going to just say that the thing we're interested in is a coefficient in a parametric regression model. So then how are we going to define our model? Define our target parameter. We're going to have a model-free definition of the target parameter. So this thing is called the Rubin causal model, or sometimes the naming Rubin causal model, and it's about counterfactuals. So what we have here is what we're going to call the full data. In this ideal world, we would have information on, just assume that the treatment is binary, you have treatment or comparator. If there were multiple levels of treatment, you have multiple ones of these. But let's assume that like Y1 is the outcome conceptually that somebody would experience if they were exposed to the treatment of interest, and Y0 is the outcome that you would observe if they were exposed to the comparator. And sometimes I might say control today instead of comparator, but I'm going to mean the same thing either way. So, and then we have all of their W's, or the W's are the covariates, so things like age, sex, anything you might want to adjust for, Charleston morbidity score, whatever you would ordinarily adjust for. Let's just call those W1 through WP. So in this full data, we have the W's and we have the Y under every possible level of treatment. So I don't even need a column for A, because like it's not that A is 1 or A is 0. That's about like real world data. In this full data, we just have all the outcomes listed here for everybody. So in this idealized world, if we have N people in our population and we know all their outcomes and all their covariates, and we wanted to know something like just if everybody was treated, what would the average outcome be in the population? And that would be, I'm calling it mu1 here, and that's the expected value of y1. So expected value just means I add up all these numbers and divide by n, and that's the average. And then the same if people, instead of everyone being treated, if everybody had the comparator drug, then that's the expected value of y0. It's just add up all these numbers, divide by n. And if I had those two things, then I can calculate a lot of different parameters. The ATE, the additive treatment effect, again, that's the same as the risk difference, would just be mu1 minus mu0. So in the population, the difference in the average outcome, if everyone were treated, minus the average outcome if everyone's controlled, that's the additive difference. Relative risk is just the ratio, mu1 divided by mu0. And then the odds ratio is just the usual formula, the odds for treated divided by the odds for control. And you can rearrange that to get that ADBC when you use a 2x2 table, but it's the same formula. So all we need to do, if we knew mu1 and mu0, we can calculate any of these three, and whichever one is of interest to you, we can give you one of them, we can give you all of them if we only had the mu1 and the mu0. And if we had the full data, we easily have the mu1 and mu0. So you can see this is why, like, you know, twin studies are so easy, so nice, because you think, well, the W's are all the same. So you basically are reconstructing this counterfactual data set where you have like one twin is the comparator and one twin is treated. And so then you're practically reconstructing this full data. RCTs, you think if you randomize, you're likely to get, you know, people who are identical on at least some of the predictors of the outcome, and you could line them up and you get back to this full data. So even though you may not have heard about the concept of the full data before just now, you're very familiar with it, because in your mind, like matching, you estimate is the same thing. You know, you find people who are just like each other, and then you sort of impute the outcomes. You say, well, this is the outcome under treated, this is the outcome under control. So now I can calculate these things. And that's all true. And this is really what's going on beneath the surface. Okay, but in real life, we don't get to see Y1 and Y0. And I just mentioned twin studies and RCTs as a way to sort of get back there. But you know all these reasons why real world evidence and real world data sources are becoming more and more important. You know, answer the real questions you want to answer, the availability of data, the ethics, you know all these, you can give that talk yourself. So we're going to be looking at data that are not from pristine RCTs. So now suddenly we need to get back to that full data somehow. How can we do it? And so we can explicitly say 3 things that have to be true in order for us to be able to go from data that we can collect to the full data set. And the first thing that has to be true is something that we call the consistency assumption. And this assumption is that the outcome seen under the real world treatment, the one right here, the A that I see for an individual, is the same as the corresponding counterfactual outcome in the table on the previous slide. So if AI is equal to 1, then the Y I observe is the Y of 1 from the full data. And if AI is equal to 0, the Y that I observe right here is the same as the Y of 0 in the full data table. So at first that seems like almost like a tautology, like of course that's true, that if you treat it, that's the one you see. But it actually isn't. I don't know if anybody listened to last week there was a mini symposium on real world evidence that Martin Ho was the first speaker, and then there were 2 others from industry, I think. And I think all 3 of them were talking about how in the real world, you sometimes see outcomes and they're recorded. It's not like they're missing in the sense that they're not written down, but they don't correspond to the treatment of interest. So for example, if if you had, say, baseline therapy and you're interested, like what happens if I add, you know, Plavix to aspirin instead of just aspirin alone, and you're going along in time and then the background therapy changes, and then you can write down an answer of what someone gets, or somebody stops taking the Plavix even though you assigned them to have the Plavix. You might still be able to measure, you know, did they have a MI or a stroke? You might be able to see that, but it's not actually the outcome that they would have had they actually stayed on the Plavix and aspirin like they were assigned to. So those intercurrent events are the very things that threaten, that undermine the consistency assumption. And so if you don't have this assumption, then you have to do something about it. You have to face the fact that the Y that you have right here in your data is neither of the Ys in that full data set. And so you've got to just treat it as if it's missing, even though it's recorded. And if you have enough information in the Ws that you've collected, then this is not a problem, and we can handle this with TMLE. So, and if you just ignore this and pretend just pretend that the Y you observed is the Y you meant to observe, then you are going to get a biased estimate of the effective treatment. And okay, so I'll move on. The next assumption is something that's called coarsening at random, and basically you can just think of this as no unmeasured confounders, and it's very closely related to that missing at random. So it just says, so I'll just leave it at that. So we need to measure the confounders for this to work. And then finally, we need to have what we call the positivity assumption, that within all levels or straight out of the people, within all people, we need to have some of them are treated and others are not. So if all these three things are true, then we can go from the data we actually get to, you know, have in our data sets the YAW for everybody. And we can manage to get back to that counterfactual data or the full data set. And if any of these things aren't true, then you can't. And so then you just sort of have to say, like, you know, you'll see in papers like, we were unable to adjust for smoking because it was not in our data, or we were unable to adjust for SES or whatever. And so you just have to understand that you can't do it. And again, instead of brushing it under the rug, you just have to explicitly understand, and that will maybe help you better interpret the result that you get from a statistical analysis. Okay, so we have our data, and now we want to estimate causal effects from it, and let's assume all of our assumptions are met. So I want to talk a little bit about the likelihood of the data. So we have the probability of the outcome given the treatment that you got and your covariates. We're used to that. And in the TMLE world, we're going to call that Q of Y. So don't ask me why it's called Q. I don't know. It just is. So there's the Q of Y is just the distribution of Y in the world where people are treated or untreated, and it depends on their covariates. Then you have this thing here, the probability of being treated given your covariates. So that's like the propensity score, right? It's the distribution of treatment among the people. And then finally, you have the distribution of people. Is your population elderly? Is your population, you know, biased? I mean, not biased, but like more male than female, more, so how, and this is just how it describes your population. And the treatment effect is obviously going to be different depending on what population, or often it's going to be different depending on what the population is, the distribution of people in your data. So Q of Y is the distribution of the outcome conditional on treatment of covariates. And then Q of W is the joint distribution of the covariates in the population. And so those two things are what we had and we needed for the full data in order to you know, be able to say our thing that we're interested in is a parameter of the full data. And this is what we had in the full data. So the Q portion of the likelihood is the portion that you really need to evaluate your parameter of interest. And then what we call in the TMLE lexicon, what we call G, in our ATE example, is going to be the conditional distribution of treatment. So you're going to see that we're going to use that. It's going to make our estimator more efficient, have smaller variance. but it's not the part that you actually need to evaluate the parameter. So when the causal assumptions hold, we can estimate the causal effect by evaluating a mapping from the observed data to the underlying parameter of the true data distribution. So all that really means is that we can kind of reproduce that full data, and then for the case of the ATE, evaluate mu1 hat, mu0 hat, and take the difference. Okay. So what's special about TMLE is that we're going to do this in such a way that we really, really try to get an unbiased estimate of the parameter of interest and also reduce the variance as much as possible. So TMLE is what's called double robust. It's going to be consistent. You're going to get the right answer if either the outcome or the treatment assignment model is correctly specified. So in contrast, if you're going to use some outcome regression model, like a logistic regression model, you actually have to get the model right in order to estimate the parameter consistently. And consistently means that as you get more sample size, the estimate goes towards the truth. And if you're using something like an IPTW estimator, you have to get that propensity score right. That's what the treatment assignment model is. It sort of is the thing that gives rise to the propensity scores. But with TMLE, you're going to get two chances. If you get either one of them right, you're going to actually converge to the right answer for the parameter of interest. And if you get them both right, then you're going to be as efficient as possible. That means smaller variance and tighter confidence intervals. So also TMLE is going to offer a valid inference, so you'll be able to estimate those confidence intervals and test statistics and p-values accurately. These are all theoretical, sort of asymptotic results, but there's also a lot of things that have been incorporated into TMLE, so it has really good finite sample performance that I won't have time to talk to today, but there's lots of bells and whistles that I'm not going to talk about today that make these guarantees happen really nicely when you're analyzing real data sets. Okay, so how does TMLE work? It actually works in two separate stages. So in the first stage, you model the outcome. And instead of using a logistic regression model, we really recommend that you use something that's more data adaptive. And so super learning is this ensemble machine learning algorithm that is very, very flexible and is more likely to get you an accurate model than if you just stick with one particular logistic regression model. Mark also mentioned on the last call that there's something that's highly adaptive. Lasso is another method that can be very flexible in getting the right answer. So we're going to flexibly model the outcome. And once we flexibly model the outcome, we're going to just get out the predictions, the y-hats for everybody if they were treated and if they were in comparator. Because you can do that with a model. You could do that with a logistic regression model as well. You don't just have to look at a coefficient. You can get all the predictions out for the y-hats when you set A to 1 for everybody, and you can get all the predictions out when you set A to 0 for everybody. Take the average and then subtract them to get the ATE. So that's a good first step. And you can say, well, if I can do that, why don't I just stop there? You just told me that Superlearner and HAL are these really great regression, can really estimate that regression, right, that outcome regression. So why don't you just stop right there, evaluate the ATE, and you could be done. You could do that, except for two things. It just might be that you got that wrong, or especially in a high dimensional space, those approaches are going to sort of maximize what's called a global likelihood. Logistic regression is going to do the same thing. If you have a logistic regression model with 100 covariates in it because you've got this enormous sample size with maybe 1 million observations, logistic regression is going to give you answers for those betas that maximize a global likelihood. But honestly, we don't care about 99 of those betas. All we cared about was the one in front of A. And so wouldn't you trade off, just like, wouldn't you like that one to just be a little more accurate and a little more precise, even if the other ones were less fuzzy. You know, sort of like when you focus a camera, you can get the whole thing in focus, or you could get somebody's face and let the background be blurry. If the thing you cared about was the face, if the thing to care about is the treatment effect, let's let the rest of it be a little blurry. So that is what stage 2 is going to let us do. We're going to update that initial model just a little bit. We're going to use information in the treatment mechanism. And we're doing it partly because if we got the initial model wrong, here's a chance to fix it. And partly because we can just shift the focus a little bit, do a slightly better job for the thing we care about. So the only thing I want to tell you on this slide is these Qs. A bar means it's going to be the expected value. That's like the y hat. The y hat, when A is 1, this is the same in this example. This bar Q n 0. So the little n means that we're getting an estimate from data. 0 means it's the first estimate we're getting. And 1W, and the bar, this whole thing means it's the y hat when I set A to 1, and I get out the predicted value from my regression model. And the same thing here. This bar QN0 just means it's my initial fit from data when I set A to 0 and, you know, these covariates. Okay, so we get what stage 1 is, and now we know why we're going to go on to stage 2, because we have a chance to just do a little better for the very thing we care about, the ATE. Okay. So I just said this. We're going to target the initial estimate of Q to reduce the residual bias in our parameter of interest. Psi is the parameter of interest. N means we're estimating it. And I put ATE up here just to remind us that we're interested in the ATE. So targeting gives us a second chance to get it right. If the outcome regression model is wrong, we use the information in the propensity score to reduce the bias in our estimate. And even if the model is right, in a high-dimensional setting, we may be able to make a better bias variance trade-off for the parameter we care about. So this targeting step is going to improve a poor initial outcome regression fit. And it's also going to leave a perfect fit alone. And that almost seems like magic, but we're going to see it in action in a minute. Okay, so intuition behind the targeting step. So conceptually, here's what we're going to do. There's a few differences. We do it on the logit scale, but I just wanted to make it simple. So conceptually, what we're doing is we're taking the residuals from the initial outcome regression, and we're going to regress those onto a covariate that we're calling H. And H is a function of A and W. H is actually going to be a function of the propensity score. So then we're going to say that, so this is the regression model. So Y is going to be our initial outcome plus some function of the propensity score times epsilon. And epsilon, so we call this thing a submodel, and epsilon is a parameter that we want to fit when we do this regression. So I'm going to tell you what H is on a different slide. It depends on what parameter you're actually interested in and the loss function, how you're going to fit epsilon. And we're going to use maximum likelihood estimation to fit epsilon. Again, I'll tell you what H is in a couple of slides. But the idea is that we take the residuals and we're going to regress them onto something that's a function of the propensity score. And that is going to give us an opportunity to reduce bias in the ATE estimate. So once we do that regression, epsilon, we just get a number for epsilon, 0.01, like whatever the coefficient comes out to be. And then we update our initial fit. We say that our new y hats are going to be the old ones plus the epsilon that we got, the 0.01, times the covariate. So we had our initial outcome regression, and now we have an updated version of it. So here's the genius part of it. If the initial outcome model was correctly specified, then there's no signal in those residuals. The y minus q, the residuals right here would be the y minus q from the initial outcome regression. There's no signals, it's just random variation. When you just regress random noise onto anything, there's no signal there. And so epsilon hat, when you do this, it comes out to be very close to 0. And that's not just theoretically. Like in real life, if you do this, it comes out to be a number very small, 10 to the minus 6, 10 to the minus 9. So if the initial outcome regression model is right, there's no signal in the residuals. Epsilon is almost 0. So that means this was right. This is almost 0. So this thing hardly changed from the initial. But now suppose the initial was just wrong, and there is still signal in the residuals. There's things going on. The covariates in the treatment still predict something about the residuals that wasn't handled already in the outcome regression. Well, in this case, epsilon hat's not going to be 0, and it's going to be proportional to the strength of the signal in the residuals. So if you had really strong residual confounding, like if you start with a completely unadjusted estimate here, if this thing was just like initial regression of y on A, and then you got the fitted values out from that, so all the bias is still there, there'd be a lot of residual confounding, and so epsilon hat would be a pretty big number, like, 0.1, 0.2, and you would get a large update to the initial. But if there's only a really tiny bit of signal left in the residuals, then epsilon hat will be, a smaller number, and so you'll get a smaller update. So weak residual confounding ends up with a small update to the initial outcome regression. So that's the intuition. That's what's going on. A lot of bias remains, we'll update a lot. A little bias remains, we'll update a little. No bias remains, we hardly will update. We won't change it at all. Here's a picture. I generated some data, 500 subjects, and here's the first 20 subjects. And then I fit an unadjusted initial regression model, and I'm just plotting what are the y-hats from the model when A is set to 0 for the first 20 people. So for this person, the model predicts that their outcome is what, negative 0.7 or something. This person's outcome is 2 when they're not treated. So that's what the dots are, the gray dots are in this left side. On the right-hand side, these are the predicted values when they are treated. So you can see the first one, they had been like negative 0.7, now they're above 0. But that person who was up at 2, they went down when they were treated. So these are the first 20 subjects, the y-hats under treatment for the first 20 subjects. Okay. And that's what this says. Initial estimate of the counterfactual predicted outcome based on a misspecified model for the initial Q when A is set to 0 and when A is set to 1. Okay, then I do the targeting step. And when I target, and then I get out my new set of counterfactual predicted outcomes from my updated estimate of the Q, and this is the Q of Y that we're talking about, you can see those are the red dots. And you can see that on the left-hand side, the new predicted values are all just a little less than they were based on the initial regression. And on the right-hand side, the predicted values when people are treated are all a little higher than they were based on the initial regression. So everybody just was nudged a little bit in opposite directions, whether they were treated or comparator. So that's what targeting does. It just nudges the predicted y-hats a little bit. And then in this particular data set, one sample, 500 observations, the true value is 1. If we had just evaluated psi of the initial, the misspecified model, we would have gotten an answer of 0.72. The right answer is 1. But after targeting, we get an answer of 0.93. So we've come much, much, much closer to the truth. And the reason we're not exactly at 1 is because in any sample of size 500, you're not going to, recover the exact population statistic that happens with all analyses. So I'm not showing it, but you can do this hundreds or thousands of times, and then you see that you on average, you get an answer that's very close to 1 after targeting. So that should convince you that targeting can be helpful, at least from an initial outcome model is not correct. So now we need, for some people in the audience, this intuition is all well and good, but what's really going on? Where does H come from? And how isn't there's some theory, like, can't you explain it to me just a little bit? So that's what I'm going to try to do in maybe the next 10 minutes. So we've got about 4 slides that are going to be a little more theoretical than what we've talked about so far. And we're getting at, you know, what's H? That's like the big mystery. So before I can tell you what H is, I just need to remind you about an influence curve, which an influence function, same thing. So the influence curve is a function that describes estimator behavior under slight perturbations of the empirical distribution of the data. So you could think, you know, when you sample data and you analyze one sample, and then if you actually do that exactly the same thing again, you take, like, say, a different 1,000 observations from this very same data, you get a slightly different answer. So that's because the empirical distribution of the data in one sample of 1,000 isn't identical in the other sample of 1,000. So how does that actually change the thing that you're estimating? That's the question. So the influence curve is actually a little more mathematical than that. You can imagine that you've got the data, and then if you just sort of maybe added a point mass, or, you know, maybe it's like one more person in this size n go to n+1, how does that change things? So the influence curve tells you it depends on where you add the person. So, like, imagine the mean in your mind. Say you're estimating mean height. If you add a person to your sample whose height is exactly equal to the mean height, then you haven't changed your estimate of the mean at all. It'll come out the same. But if you add somebody who's much taller than the mean, your estimate of the mean will go up. If you add someone who's much smaller, your estimate of the mean will go down. So depending on where you add them is the effect it's going to have on the thing you're estimating, the estimand. So that's what the influence curve is. It just describes how large of a change a little change in the empirical distribution has on the thing you're estimating. So that's the influence curve. The empirical mean of the influence curve for a regular asymptotically linear estimator, and most of the estimators we ever are thinking about are regular asymptotically linear. The empirical mean of the influence curve provides a linear approximation of the estimator. That means you can actually use it mathematically to estimate the parameter of interest. And then among all influence curves for all regular asymptotically linear estimators of the same parameter, the one with minimum variance is called the efficient influence curve. So there's an efficient influence curve for the ATE, and in TMLE notation, we call that D star. That's the efficient influence curve. The star means it's efficient. And it's a function of the distribution of the data, P. So this targeting step ensures that the empirical mean of the efficient influence curve is 0. And that's sort of the best you can do for estimating the parameter from these data. And then just mathematically, we write that. We can say TMLE solves. Tn means the empirical mean. D star is the efficient influence curve. T star of n is our sort of targeted estimate equals 0. So this is the equation that's actually being solved in that targeting step, or overall, that's what's being solved by TMLE. So this is the key. If you know any theory at all, this is the key. TMLE is solving the empirical mean of the efficient influence curve. Okay. So to make that a little more concrete, this is the efficient influence curve for the ATE parameter. And it's not as scary as it looks. This is Y, the outcome you observe, minus the Y hats under your observed treatment. And this part up here is basically 1 over a propensity score. G is a propensity score. So if you're treated, this part inside the braces is 1 over the propensity score, so it's like an inverse probability weight. And if you're in the comparator group, it's 1 over 1 minus the propensity score. So again, it's the inverse probability of seeing what you treated, only it's got a minus sign in front of it. Okay, so that's what this part is. It's sort of an inverse probability weights multiplied by the residual. That's that part that I'm calling A. On the right-hand side, that's actually much easier. This is the Y hat when you're treated. This is the Y hat when you're comparator. And this is the parameter that you're being estimated. I'm calling this the B section of this equation. So this entire thing is the efficient influence curve for the ATE parameter. I told you in the beginning, and we want this thing to have mean 0. If we can arrange for this to have mean 0, then we will have solved that the empirical mean of the efficient influence curve is mean zero. And that means that our estimate psi n, when we solve this thing, is going to be the best we can do in these data when we get the outcome model right and the propensity score right. So let me remind you that we're actually going to evaluate the TMLE as the empirical mean of the y-hats, the targeted y-hats when A is set to 1, minus the empirical mean of the targeted y-hats when A is set to 0. This is the mu1 hats, and this is the mu0 hats. Mu1 minus mu0 is our estimate. That's what this part is. This is on average is going to be the mu1, and on average this is the mu0, and then this is going to be our estimate. So on average, this thing has mean 0. That means this B portion already has empirical mean 0. I want the whole thing to have empirical mean 0. So if this has empirical mean 0, then all I have to do is in stage 2, I'm going to do this, is make sure that this has empirical mean 0. And once I do that, I'm in business. I've solved the whole thing. So that's what's going on with TMLE. Okay. So targeting step arranges for A to also have mean 0. And you already saw we defined this parametric submodel that Y is going to be epsilon times H plus the offset of the initial regression. We're going to use maximum likelihood to fit epsilon. When you do maximum likelihood, this is regular ordinary maximum likelihood. What happens is the variable times the residuals is going to sum to 0. So this right here is the residual. This Qn star is the epsilon H plus offset Q. So the epsilon is implicit in this notation. It's right here. We're going to fit epsilon so that epsilon H plus offset Q, Y minus that, times H has sum 0. That's what MLE does. Those are the score equations. Oh, I wrote it here. The Qn star is the epsilon H plus Qn 0. Okay, so let me say it again. We're going to define this model. We're going to fit epsilon by maximum likelihood, and epsilon is going to solve this. Our goal is to make sure that this thing has mean 0. When we fit by maximum likelihood, this thing's going to have mean 0. We get to choose H. It would be oh so convenient if we choose H to be this part right here, the A over G minus 1 minus A over G0. If we choose that, then when we fit by epsilon, we're going to be guaranteed that this part has mean 0 at the updated Q. We'll make sure at the updated Q we'll evaluate this. The whole thing has mean 0. So that's the trick. That's the secret. That's what's going on. The targeting step is regressing the residuals onto this covariate in order to make sure that this thing has empirical mean 0 at the updated outcome model. Then we're also going to make sure that we use the updated outcome model to evaluate this part, so it'll have mean 0. So the whole thing is going to have mean 0. We get to choose H. It's easy to choose. You look at the efficient influence curve, and this is the H you choose. If I had a different parameter and I put a different efficient influence curve in front of you, but there's always a Y minus Q here, the H you're going to choose is whatever's in front here. And if you choose that, then you're in good shape. So that's why I said my goal was at the end of this, you have enough insight so that you see the math might get trickier for different parameters. It can get trickier, but if someone gave you the efficient influence curve equation, you could pinpoint H yourself. Okay. Oh, so then because of this asymptotic linearity thing, it has a lot of like nice properties. You don't have to do bootstrapping to find out the variance. You can estimate the variance. So what this says is that the difference between the estimate we get and the truth is going to converge in distribution, times root n. It's going to converge in distribution to something that's normally distributed, mean 0. So the difference is going to be small, go to 0. And it's going to have variance sigma squared, where sigma squared is the variance of the influence function. So you can construct confidence interval the usual way. And you can construct test statistics for null hypotheses the usual way, and p-values just the usual way. And the math might look daunting, but this is, once you get the variance estimate, it's the usual math you always use for confidence intervals, test statistics, and p-values. All right, the theoretical part is over. So now we get back to the part that's a little more accessible to everybody. So usually at this stage, it's time to give an example. But I know that by the time I'm 50 minutes into listening to a talk, I really can't understand the example anyway. So I thought what I would show you instead is just some very recent, last year or two publications, just to give you the idea that TMLE is not just something that's in the research labs. It's actually out there being used. Here's some examples in EPI journals, Journal of Environmental Research and Public Health, Policy, Social Science and Medicine, Clinical Outcomes. Oh, in fact, we're going to have a talk on this in a couple of months. This exact article, we're going to have a talk by David Benkisser, who's the statistician on this paper. The talk will be in this webinar series. So TMLE is being used in practice to answer real questions in the real world. And the other thing I want to tell you, just a few more things, is that hopefully now TMLE makes a little bit of sense. And let me just go over what we did today. Stage one was easy. Use some flexible estimation procedure to estimate the Q portion of the likelihood. And the real big thing is estimating that outcome regression. Because the QW part is pretty easy. When you take a sample, once it gets large enough, it reproduces the distribution of covariates in the population of interest. So we have already a good handle on the distribution of people in the population you care about. But you need to flexibly estimate that outcome regression. Okay, that's still, though, easy for you to understand. The second part now should make sense. We're just going to tweak that initial estimation of Q a little bit to update it to get a targeted Q, and then the star just means it's targeted. How we do it is we make some use of the information in the G portion of the likelihood. For this example, it was the propensity score. We create this covariate H, and exactly what it looks like depends on the thing we're estimating. We saw how to do it for the ATE today. Oh, and then this is just to give you a sense, when there's lots of follow-up, there's the word up is missing. When there's lots of follow-up, then not only would G include the propensity score, but we'd also include sort of like those inverse probability of censoring weights, like the missingness or the rate censoring mechanism. And so because we're using information from all these parts of the likelihood, that's going to generally help with efficiency, and it will help with bias when we need to help with bias. So it provides an opportunity to improve the estimation of the parameter we care about, the true parameter psi 0. It's going to reduce the asymptotic bias if the initial QN is not consistent. So if we made a mistake with our initial outcome regression model, it's always going to be biased. And targeting will help with that. It also can reduce just finite sample bias. The outcome regression model may not be terrible, it just didn't quite get to the right answer yet. And often targeting will reduce variance as well. And then the other thing I want you to know, after you have this targeted estimate Q and star, you're going to evaluate psi by just plugging it into the formula for the ATE, the formula for the outcome, for the odds ratio, the formula for the risk difference, the formula for the hazard ratio, the formula for whatever it is you want to estimate, the ATT. There's going to be a formula for it, and you'll plug it in. So that's why TMLE is sometimes called a plug-in or a substitution estimator. Okay. The next part of the concluding remarks is that you're going to, I don't know about you personally, but the world in general is going to be relying on this real-world evidence to answer complex real-world questions that we all have. If you're going to be doing that, you need to be thinking from a causal inference perspective. And then I would argue that you also need to be taking this flexible approach and you need to be thinking about what is it I really care about estimating. And so targeted learning is going to combine that causal inference framework with state-of-the-art estimation techniques. And that's why we're having this whole webinar series, so you can keep hearing this message and see different ways that people are doing this in real life. So TMLE has superior properties for estimating point treatment effects compared to, say, matching or IPTW or just straight parametric regression modeling. So I'm going to always encourage TMLE use. But what I want to say, even though I didn't talk about it today, is that it's actually essential, in my view, for longitudinal data analyses. It's going to help you appropriately adjust for bias due to informative dropout, and also to those consistency violations due to post-treatment intercurrent events. And what we're going to do with those consistency violations is really just say, we don't see the right outcome, so we're going to think of it as that outcome is missing, but we're going to be able to re-weight. As long as we have the reasons for the dropout, we'll be able to re-weight to get us back to that full data where we should be. So if you don't do TMLE, like if you just did a Cox model, you can't, I know there's time-dependent Cox models, but then you get stuck with, if you try to adjust for something in the model, then you're adjusting away part of the treatment effect, or there's that potential. And if you don't adjust for it in the model, then you're actually not adjusting for the bias that is introducing in you know, due to the missingness in the outcome. So with a time-dependent Cox model, you still need some notion of things happening completely at random. That probably isn't true in the real world. So you need to use something that's more sophisticated. There's marginal structural modeling, but again, that brings you back to a parametric modeling world that you might want to avoid. There's some other G computation methods, but they might not be flexible when it comes to superlearning. And so I think that TMLE is going to be the right balance for longitudinal data analyses. But you have to use something more sophisticated than just a Cox model, unless you don't mind the bias. Another thing TMLE will let you do is if you have more complicated questions, like if you want to understand the effects of dynamic treatment strategies, where decisions at some time t are based on the treatment history and the side effects and the intermediate outcomes that are measured all the way up through t-1. So that's the way a lot of medications are actually prescribed in real life. You know, the doctor starts you on something, then you have side effects. It has, you know, it's not working to you know, it's not lowering your blood pressure effectively. It's not treating your depression, whatever. So they try something else. So you sort of want the whole entire path to be taken into account as you figure out the effective treatment, or maybe even what would be the optimal treatment decision. And to do that, you really need TMLE. There's packages to just do that let you do it. And so that's why I say it's essential for longitudinal data analysis to do something like this. And then even though it might have sounded a little scary, I really just encourage you, it's not, just try it yourself. There's on CRAN, there's a TMLE R package for estimating point treatment effects, like I talked about today. The ATE, the relative risk odds ratio, ATT, the average treatment effect among the treated, ATC, and that additive treatment effect among the comparator, a dose response curve. You could do marginal structural models and control direct effects. And all you have to do is download the package, run a few examples just to, or do your own data analysis. You don't have to be scared of this. It's fun and interesting. For longitudinal data analyses, there's our package called TMLE, and the L for longitudinal. And it lets you estimate hazard ratios, survival curves, difference in survival, effects of dynamic and static treatment strategies, and marginal structural models. Both of these use superlearning. There's a superlearner R package that does regression and classification that we use to estimate the outcome regression and also propensity scores. And that's also on GitHub. And then finally on GitHub, there's a whole repository called the TLverse that not only has even more advanced tools for targeted learning in R, but also workshop and course materials. So I encourage you to look that up as well. Thanks for joining, and see you next time.